Hey! Hi! So, every magnetic pole that you've ever held in your hands is actually a dipole. It has a north and a south pole. And no matter how much you truncate it, you reduce it, there's always a north or a south pole that is being born again. But today I want to explore the hypothetical scenario. Hypothetical or not, we have yet to discover whether it's hypothetical or real. So today I want to explore the possibility and what it actually entails for a magnetic monopole to exist. So yeah, let's go. So let's start with something simple. Magnetic charges don't exist alone. Electrical charges can exist alone. For example, we have an electron. An electron is a point of negative charge. We can pinpoint to the electron in simple terms and say that's where the electrical charge is coming from, right? But with a magnetic field, we can't really do that. A magnetic field is a loop from north to south or south to north, whatever you want to, whatever convention you're choosing. So there's no start and no end. It's just a full loop. That's not just a coincidence. In fact, this is a perfect consequence of Maxwell's equation. Yes, this video is also a trap for me to explore what Maxwell's equations are. Let's start. So the first Maxwell's equation that we were gonna talk about is the divergence of the magnetic field is equal to 0. And why this is very important is because these equations all have a constant on the right hand of the equation, except for the ones relating to magnetic charge. Now what I mean is that, in plain English, what I mean is that magnetic fields, lines, they never pinpoint to a certain point in space and go this is where the magnetic charge is coming from. Now, if I'm going to put a graph on the screen right now, it's going to show you. Yeah, I hope I'm not just showing my hands around. Yeah. So according to Maxwell, which we're going to explore in further depth just a couple of seconds from now, is that magnetic charges, they don't exist. But today's video is not just about that. We're going to explain what if they existed? What if magnetic monopoles existed, just like electrical charges? So for that, we need to explore Maxwell's equations. So these are the 4 Maxwell's equations. And the first one just means that electrical charges create electrical fields. Very simple. The second one just shows us that the divergence of the magnetic field is equal to 0, and in plain English, like I explained just earlier, it means that magnetic monopoles, they don't exist. Simply, they don't. And for the third one, it just means that changing the magnetic field, it creates an electrical current. And for the fourth one, it's the same. Currents and changing electrical fields, they create magnetic fields. Simple. There's also lots of math in here, and if you want to go in depth about the explanation of divergence and curl, and what is that triangle thingy, it's the del operator, it's a vector operator, and so on. If you want to know more about that, I highly recommend the first chapter, I think, of David J. Griffiths' Introduction to Electrodynamics. He gives out very simple explanations and accompany it by good problem sets, I should say. And it's really an overall amazing book. It's really critically acclaimed by the physics community, and personally I'm going through it right now, and it's really amazing and I really like it. It's giving me an ego boost almost. I'm really excited to delve more into electrodynamics. Classical electrodynamics is coming next, so yeah, I'm really excited. Anyways, tangent of the side, let's continue. Now, we just explained what Maxwell's equations mean. Let's see what we can do with them. So what we can do with them is that if you notice Maxwell's equations, there's a bit of dissymmetry, like I said. There's a part of the equation where we have a constant on the left hand, the right hand of the equation, next to the equal sign. Well, yeah, both of them are next to, but the divergence of the electric field gives us a constant. However, the divergence of the magnetic field, it gives us 0, and that creates a bit of dissymmetry. So what if we postulate that the divergence of a magnetic field, just like the divergence of an electric field, it also gives us a constant. This would gives us a second set of equations, and this would entail the creation of a magnetic monopole. This is the new equation. The divergence of the magnetic field is equal to nu 0 times rho of m. So, the new equation says that monopoles would make magnetic fields the same way that electric charges make electrical fields. Yeah, we made it. But there's a consequence from this. If you want to get into the math of it, I won't be doing that in this video, but if you want to do that, I highly suggest that you read, Introduction to Electrodynamics by DJ Griffiths. It's really good. It gives us this new equation. And normally, the curl of the electric field is equal to minus the derivative of the magnetic field over with respect to time. It means that changing a magnetic field creates an electrical field. But in this new way that we rewrote it with the new constant that we've given, it means that the effect of moving little magnetic charges, it creates the electrical field, not the movement of magnetic fields that creates electrical fields. No, now we have little charges, and those little charges are the ones responsible for the electrical field. So that's something, right? And why does this matter? Well, it's actually very important, and I'm going to discuss this later on the part of consequences of this, and what theories use this generally. So, Paul Dirac, actually, he's a very well-known physicist in 20th century physicist, and in the 1930s, he postulated that magnetic monopoles could exist, and that would help us understand the quantization of electrical charges. And it's a really interesting bit of information, but that would have to require us to delve into quantum. And I'm not really well versed in that, and I don't trust myself to explain it well. So let's move on. So one part of understanding why electrical charges are exactly the way they are, the elementary particle charge E is equal to 1.602 to the power of minus 19 coulombs. Why is it like that? And so on. It's actually related to quantum mechanics and Paul Dirac's postulation of magnetic monopoles. So, what I wanted to get into is how do we observe these things? How do we make sure that this part of physics is actually real? Well, we actually build so many things, like the Large Hadron Collider, the LHC. We also have things like the cosmic ray detectors, superconducting loops, and so many other things. We also have theoretical methods, and as well as analytical and empirical methods with experimentation and so on. But so far, we have found nothing, and it's really bizarre because they have to be somewhere, right? Maybe not. I don't know. Maybe they're hidden in the beginning of the universe, in the Big Bang. Maybe they're somewhere there, maybe, because the grand unified theories and string theories, they kind of predict that they must exist, and yeah, maybe they're, like I said, maybe they're hidden in the early universe, maybe at the very start of the Big Bang, or maybe somewhere around there. Who knows? And if we discover just one singular magnetic charge, it would be revolutionary. We would have to rewrite all of our textbooks, and the beautiful Maxwell equations need to be rewritten, and we'd have more beautifuler Maxwell equations with a bit more symmetry going on. In conclusion, there's just more to physics that we have to yet explore, and the most beautiful part of physics, in my opinion, is how much we still haven't found and the mysteries around that. but also how we did find these things. The universe is really huge and we're really tiny, and human ingenuity can go so far, but our ingenuity going this far, it's really commendable, and I really hope that something happens with magnetic monopoles, and maybe something did happen and I'm just not aware of it. But yeah.